Welcome everyone to this class on linear regression using R. This will be the closing class on linear regression. Hopefully, if time permits, we will also touch upon an introduction to logistic regression towards the end of the class. There were some pre-work expectations in terms of installing R. If you were able to do that, that's great. If not, that's perfectly fine. Now, what we're going to do is, in case you have not done that, you can always practice later. Before I make Ujjwal the presenter, I hope some of you have had a chance to look at the new LMS link that we've shared across with you earlier this week. Ujjwal will just show you the link page and how to actually access the materials and presentations after I make him the presenter, which I'm going to do now. So give me a second here. Over to you, Ujjwal. We've just made you the host.
Sure, Amit. I'll just quickly share my screen. Okay, so I hope everybody is able to see my screen, guys. If yes, can you please quickly type a yes into the chat window? Great, great. Okay, so guys, this is the new LMS link which Amit has shared with all of you. Okay, and let me just quickly paste it here for your convenience so that all of you can access this link. As you can see that the link has multiple sections. You first have a video section which contains the recording of what we have done in the lecture. Then you have the presentation associated with that particular lecture and any data or data set which you guys should be expecting what we practiced in the lecture. Okay, so for example, today's session is session 9. The lecture which we'll be recording will get will be available over here after we are done with it. Since we don't have any presentation, you might not find anything in this section, but all the data sets and the codes which we'll be executing during the lecture can be downloaded from this section. So if you'll go to download data, it will take you to a Google Drive wherein you'll have all the sample codes, the CSV files, and all those which are required for today's lecture. Okay, I hope everybody is clear with that. And if everybody is, then let me just quickly take you through another small section which I think will hold it's going to be very important for all of you. Look at this section out here, that's installation guide. Okay, over here you will get to see how to install Excel, RStudio, SAS University Edition, and Tableau. Okay, so all these guides are readily available for you. In case you haven't installed R for today's class, that's absolutely fine, but I would request all of you to please make use of this guide and install R or any other language which is required for the future lectures. Okay, I think we currently have 9 participants in there. Let us wait for 5 more minutes for others to join in, and once everybody else joins in is where we will get started. Thanks a lot, Sundaram. I hope everybody else also liked the new LMS which is there. Okay, so let me just quickly open the Excel sheet which we'll be using today. That is cars.csv, our favorite old data set which we'll be making use of. Great. Okay, guys, I would request that we wait for another 5 minutes because we are still expecting a few more people to join in, and once everybody joins in is where we'll start. Okay. Uh, Sorry guys, we just got to know that a few of us are not joining in for the lecture today. So I think if they are not, then let's get started with today's lecture. Now, before I get into what I'll plan to cover today, let me just quickly ask some questions. Okay, some revision of what we did in the last lecture. Now, can somebody quickly tell me that how the equation of regression model would look like? Can you quickly type it into the chat box? What is the equation of regression model? So Hiroki says ax plus b, Sridhar mx plus c. Very nice guys. What about others? Everybody's fine with that. Great. Okay, so it looks something like this, as a lot of you mentioned. Y is equal to mx plus c, where x is my, what is x guys? Is it an independent variable or a dependent variable? Good. X is independent and y is my dependent variable. Okay. And out of my regression process, what I tend to find out is the value of m and the value of c, where c is my intercept and m is the slope of a line. Okay, so what regression model tends to give us is a straight line using which I can predict the value of of a dependent variable by means of independent variable. Okay, so this is what we talked about when we started with the linear regression in the last class. Okay, then we also tried executing a simple linear regression. But before I get into that, can somebody tell me the difference between simple linear and multiple linear regression? Simple linear regression and multiple regression. Can somebody quickly tell me the difference? Okay, Hiroki. So number of independent variables. How does it relate to simple linear or multiple linear regression? Mm-hmm. Okay. So guys, I think all of you are almost there. Hi, Karina. Welcome to the class. Uh, don't worry, we haven't started yet. We are just refreshing of what we did in the last class, and so you haven't missed anything much. So guys, simple linear regression is where you just have one dependent variable, independent variable. Yes, and in multiple linear regression, you have multiple independent variables. Okay, so this is the difference. Now let's understand how we ran a simple linear regression the other day. Okay. So guys, where did I really go in the Excel sheet to run the regression equation? Which tab? Was it insert, page layout, formula, data, review, view? Where exactly did we go? Very nice. We went to data, and then we went to data analysis. And once we went there, we picked up regression. Okay. And we said, okay. Now input Y range is nothing but the range of my dependent variable. In this case, my dependent variable was miles per gallon. That's the mileage of the car. My X range was nothing but my range of independent variable. I think last time we did it on the basis of weight of the car. So that's what I'll pick up now. And obviously my data had labels. So I selected that, and yep, that's it. And I just ran it. Okay. And this is the output which we got. Now, I hope that all of you remembered the outcome which we worked with last time. Why can't I see it? Okay, so guys, can somebody quickly tell me what is R square? Can somebody try a hand at it? Very good, Sridhar. Yes, that's the percentage by which we improved our model if we never had any factors. Kaustup says percentage of correctness, coefficient of determination, absolutely fine. Absolutely correct. Great, guys. And can somebody try and tell me what is adjusted R square, guys? Guys, adjusted R square? Okay, this is R square. Exactly, Hiroki. Very nice. R square is the adjusted R square is R square adjusted for number of independent variables. Okay, now if the inclusion of an independent variable doesn't add a lot of value to my R square, in that case my adjusted R square will go down. But if it proportionately adds value to my R square, my adjusted R square will move in sync with my R square. Yeah, all of you remember we discussed this? Yes, no? Great, great. Okay, and then we talked about, this. Karina, I believe you were not there in the last lecture. I would request you please refer to the last lecture video to understand this, because I've already explained it in detail in my last lecture. Yeah, I hope you'll be okay with that. Okay, but for now just keep this in mind, that your R square and adjusted R square should be as close as possible. If you see a lot of difference between these two, it means there is something not right with your model. Okay, there are certain independent variables in your model which you might have to drop. Okay, because they are not adding value to your predictability. All right, just keep this in mind as of now. Okay, now higher the value of R square and adjusted R square, it means better predictability of your model. Okay, all right, and once we understood what is R square and adjusted R square, we talked about this ANOVA table. All right, now guys, what was the hypothesis of our ANOVA table? Can quickly somebody tell me? What was the hypothesis which we tested from this ANOVA table? Somebody? That the model is independent of any factors. Absolutely, Sridhar. Or in other words, I can say that my slope in the model is equal to, guys, the slope in the model is equal to 0. Great. So if the slope of the linear equation is going to be 0, then whatever be your independent variable, okay, it means this independent variable will never have any impact on your dependent variable, right? Right, and that's what we are trying to test by this ANOVA table. Okay, so now if the value of significance f turns out to be less than 0.01, okay, in that case we will reject our null hypothesis, okay, and say that the slope is not equal to 0. It means my model is okay. Okay, but if this value of significance f turns out to be greater than 0.01, in that case I cannot reject my null hypothesis and my model is not good. I cannot go ahead with model. Guys, could you recollect everybody? Yes, great. So when we ended our last lecture, we talked about three things. One, R square. We say that bigger the R square, better it is for us. Adjusted R square. Exactly, Sridhar. Yes, the value of significance f has to be less than 0.01 to reject the null hypothesis. Okay, adjusted R square, where we talked about how R square get penalized for every new addition of independent variable in my model. Okay, so we always expect r square and adjusted r square to be as close as possible and as high as possible. Okay, and the third thing we talked about was ANOVA table, wherein we said that if the value of significance f is less than 0.01, in that case I'm good to go ahead with my model, and if it is not, then I cannot go ahead with this particular model. Okay, these are the three things we did in the last lecture. Okay, now the only table which is left from regression is this particular table. Okay, now guys, can you see there is something written over here? Any guesses? What is this intercept and what is this weight and what are these coefficients? So first tell me, what is this value 46.21? Can anybody guess what is this value of 46.21? Very nice, Hiroki, very good, Chandra. Yes, these are the intercept values. This is, so when I write this equation y is equal to mx plus c, this c is what is denoted by coefficient of intercept. So this value out here is your C value. Okay. Now guys, what was X in our model which we just ran? What was X in our model? Hiroki says weight. What about others? Was that weight really? Everybody? Guys, yes, no? Yes, Kaustubh, that was the independent variable. But what was independent variable which we considered when we ran this model right now? Weight of the car, exactly. So my X was my weight, okay? And the coefficient to weight, what is this? This is your M value. So this is your coefficient of weight. Okay guys, so as you ran the model, you found out the value of M and C, right? You found out the value of C and you found out the value of M, right? So now, can I write my linear regression equation as miles per gallon is equal to minus 0.0076 into weight plus 46.21? Can I write this equation, guys? Is this the right equation to write? Everybody else? Sundaram and Kostaba, fine. What about others? Good, good. Great. But guys, before we really write this equation, Sridhar says the sum of coefficient plus 1 was used somewhere. Sorry, Sridhar, I didn't get that. Where exactly did you use this? And why plus 1? Okay, I think Sridhar, we can always take this question, after we are done with the class, because I'm not sure what really is, asked over here. Okay, so guys, before we really go ahead and write this equation, it is first of all important to see whether these coefficients can be used in the model or not. Okay, and how to test that? You check that using this p-value. Okay, again, what this table does for us is it tests the validity of each of these coefficients. Okay, it tests that whether these coefficients are significant to be used in our model or not. All right, so again, the hypothesis is that if the coefficient, sorry, if the coefficient is significant for the model, okay. So the null hypothesis is that it is not significant for the model, and the alternate hypothesis is that yes, it is significant. Now, if your p-value is less than 0.01, then the coefficient should be used in the model, okay. If the value is greater than 0.01, then we'll have to see. I'm not saying we'll remove it, but we will see. We will do further checks. Okay, guys. If your p-value associated with the coefficient is less than 0.01, go ahead and use the coefficient. But if it is greater than 0.01, don't remove it. Keep it there, but do some further checks. Do some further changes to the model. Okay, guys, is this clear to everybody? Great. So going forward, whenever you get an output like this, you'll first of all see that how good your R square and adjusted R square are. So if they are close to 0.8 or 0.7, you know that your model is able to predict 70% of the outcomes. Okay, that's the first thing which you'll do. Then you'll see that if the model is really significant, if the whole model is significant, you'll see this value to be less than 0.01. That's where you should go ahead. As a third step, you will check the p-values of all the coefficients which are going to be there. Okay, so right now we have two coefficients. When you'll run multiple linear regression, you might have multiple coefficients. Okay, you should check the p-value for all of them. All those which have a p-value of less than 0.01, you can straight away go and include them in the model. For rest of them, keep them in the model, but be cautious, and I'll tell you how to be cautious and how to deal with these going forward. Okay, so this is how you generally run a simple linear regression model. Guys, everybody clear till this point? Does anybody have any question? Quickly type a no in the chat window if you don't have any questions, and we'll move ahead. Great. Great. Okay, so now that we have run a simple linear regression equation in Excel, let me also show you how to run it in R. Okay, because our whole idea is to make use of R as the analytical tool, and let's see how to run it in R. Okay, and trust me guys, it is very simple. Where is my code? R code for simple regression. Arvind, I really understand. I think you haven't seen the previous video. I would request you to please go ahead and watch the video. These things will become real clear after that. Okay. Okay. Now, can somebody tell me that what exactly I'm doing in this part of the code, guys? If anybody can recollect. Quickly tell me, what are we really doing in this part of the code which I have highlighted? This is the one I'm talking about. Why am I not able to see the chat window? Yeah. So Hiroki says, okay, everybody's saying loading the data. Absolutely, absolutely. We are just trying to read cars.csv from my regression folder, which is currently there in my C drive. Okay, that's what I'm trying to do. And as I'll import it, I'll be able to see a variable data1 coming into my environment variable. Okay, so let me just quickly execute it and show it to you. Ouch. So it says that cannot open the connection. All right, why is it not able to open the connection? Let's see. Ouch. Okay, so I think I have changed the name of my folder, and that's why it is not able to pick it up. So this regression will change to session 3 regression, and then we will read it. Right, guys? So can you see that it was because it was an incorrect path, it didn't read it at the first go. The moment I set it to the correct path, the data got read. Okay, and as you can see that this exactly the same data is now available as we saw it in the CSV file. Okay, now how to really run the model, okay, is the next thing, or is the next question. Very simple. You don't have to do anything, just write one function. The function name is LM. Okay, LM is the function which helps you run the linear regression model. Okay, now the LM function, the bracket start and bracket ends over here. Okay, now within the brackets, the first attribute which goes into the function is the name of the dependent variable. So our dependent variable name is actual dot miles per gallon. Remember, we are trying to predict the mileage of the cars, right? So that's my dependent variable. Then comes this symbol, which you'll see on top of your tab button on the keyboard. Okay, put that symbol in there, and then write the name of the independent variable. In our case, it is weight. Okay, so what this part of the function tries telling our system is that our actual MPG is my dependent variable, weight is my independent variable, run a regression on these two variables. Okay, but then the next question which our system will ask you is where to pick up the data from. And that's where the second attribute comes in, wherein you say that data is available in data1 variable. So pick up data equal to data1. All right, and the output of this particular function, assign the output to model1 variable. Guys, is this statement clear to everybody? Why is tilda used? Tilde. Arvind, I can't see tilde anywhere. Oh, okay. You're talking about this. Okay. I'm sorry. I didn't know that the name of this symbol is tilde. I'm so sorry for that. Yeah. See, this is how this function really accepts. You know, this is the syntax basically. This is how the syntax of this particular function is, that it expects the independent and dependent variables to be segregated by tilde. Okay. Okay, great. So once we've done that, let me just quickly run this model. So guys, the moment I press the control and enter, you see you got a model 1 in there. Okay, so the model has run. And how to see the results of the model? Just write the summary function, and within summary function, give the name of the variable which contains the model. So the moment you do this, you'll get to see the output. So guys, this is where your output is. Okay, now guys, this output is not at all different from our Excel output. Okay, and I'll just prove it to you now. All right, first of all, can you see this part of the model? Does this relate to any specific part of our Excel output? Can anybody recollect? Yeah, this is exactly equivalent to the third table we discussed, wherein you had the coefficients and the p-values. Okay, so over here you have the estimate of the coefficient. So estimate over here is nothing but your coefficient, and here you have the p-values. Okay, now guys, if you look at the star marks over here, these star marks will tell you that to what level of threshold are these estimated coefficients significant. So remember we talked about comparing the p-value. We talked about comparing the p-value with 0.01. Okay, a 3-star would mean that even if you'll compare to the value of 0, these coefficients are fine. Okay, if I would have got just 1 star over here, it means I should have, if my threshold would have been 0.05, then only I would have considered these variables as significant. Can you see? A single star is next to 0.05, right? So what these star marks tell you is, you define your threshold first. Okay, now let's say if my threshold is 0.01, I need to have at least 2 stars for each of these coefficients, because there are 2 stars over here. Okay, if I define my threshold as 0.05, bare minimum I need to have 1 star for each of these coefficients. Okay, so R basically helps you in comparing these p-values to the threshold, so that you really don't have to go and check it against 0.01 or 0.05. The moment you see 3 star, you know that these coefficients are perfectly fine to go ahead with. Okay, the moment you see 2 stars, you would know that you are compare, you are perfectly fine if your threshold levels are 0.01. The moment you see just 1 star, you know that you can use these coefficients only if your threshold value is 0.05. Okay, so this is the significance of stars. All right, and then let's look at these two values over here. So the way in Excel we had R square and adjusted R square, exactly the same values are being given over here. Okay, and if you look at this last row of the output, this is your ANOVA table output, where you have F statistics and the p-value associated with ANOVA. Okay, so this is how the output of R generally is when it comes to linear regression. Guys, is this clear to everybody? Or if anybody has any questions, I'm happy to answer them now. I don't know why I'm not able to see the chat window. Yeah. Okay, so Karina says, so triple star is equal to coefficient should be used. Exactly, Karina. If you have 3 stars, it means you can straight away go and use the coefficient. Chandra has one question. The stars, can you repeat them, please? Yes, I can. Hiroki says triple star means 99.9% confidence. Hiroki, it has nothing to do with confidence. It has to do with significance. Let me just explain that. Okay. So guys, when you remember we did hypothesis testing, okay? And we said that for my null hypothesis to be rejected, my p-value should be less than my significance level. Remember everybody? Yes, good. Now, your significance level is completely dependent on how your industry defines it. So for example, in pharma, you'll have a significance level of 0.05 always. Whereas if you go to, you know, some financial, organization, they will have a significance level of 0.01. Okay. So what you do is you always check for your p-value. If this value is less than the significance level, exactly, Arvind, it is kind of an error rate. You're right. Okay. If your p-value is less than your significance level, then you say that you have rejected your null hypothesis and you're okay to go ahead with an alternate hypothesis. Okay, that's what we do. Now, what I'm trying to say is that generally an industry practice when people do regression is to keep the threshold of 0.01. Okay, sometimes people also keep 0.05, but most of the time people keep the threshold as 0.01. If your significance value is going less than 0.01, it means in this particular case your model is good. In this particular case your coefficients are significant. Okay, you should use these coefficients. Now, ouch, if you'll go to R, these star marks make your comparison simple. If you see these star marks over there, you really don't have to check the p-value and compare it to your thresholds. Okay, the moment you see 3 star marks, you can straight away assume that this coefficient is perfectly fine and good to go ahead with. But if you see 2 star marks, then you are okay to go ahead with coefficients only if your threshold is 0.01. Okay, if you see just a single star mark, then also you are okay to go ahead with these coefficients, but if your threshold or significance value is 0.05. Okay, so guys, is this clear now? Great, great, great. Okay, so as I was telling you guys that in running a regression in R is this simple. Okay, you just write one equation, summary of the equation, and you get the output. Okay, so there is no rocket science in doing regression in R. I hope everybody is okay with that statement. Great, great. Okay, now that we have run a simple linear regression, okay, let's quickly also run a multiple linear regression. Okay, let me just quickly do it for you. Now, obviously in my simple linear regression, I had just one independent variable. In my multiple linear regression, I'll have multiple independent variables. Okay, so how to do that? We'll go to data, we'll go to data analysis, we'll go to regression, my input range of y, that is my independent variable, I'll select that. Now my input x range, let's take cylinders, engine displacement, horsepower, weight, acceleration, everything. Okay, so I'm taking multiple variables now. Okay, so I've taken all the independent variables which I wanted to and just press OK. The moment you press that, you see, you've now got a multiple, you got a R square, you got an adjusted R square. Are these two looking very close to each other or different from each other? Guys, R square and adjusted R square, they're close, right? So it means the addition of variables have done good to us. Okay. Okay. So the, and how much is the predictability of the model in this case, guys? Can anybody guess? What is the predictability of my model? Kaustubh says 70%. What about others? Guys, remember we said that the value of R square tells us that how much is the predictability. Remember? Yes. So since it is 0.707, my predictability is approximately 70 or 71%. Yeah. Now tell me, is my model significant? Can I use this model? Arvind, it's 9.8 into e to the power minus 101. It's not 9.8. It's 9.8 into e to the power minus 101. Very good, Sridhar. Yes, that's absolutely fine. So since this value is less than my threshold, which is let's say 0.01, I know my model is good enough to go ahead with. All right. Now, guys, tell me, is my intercept significant? Is my intercept value significant? So rather than asking each and every variable, individual variable, tell me which all, sorry, tell me which all variables are insignificant basis the p-value. Which all variables are insignificant? Quickly tell me. She's saying all except intercept. No, that's not correct. Okay, guys, there are multiple variables which are insignificant in this case. My intercept is significant. Okay, my intercept is perfectly okay because it is 3.47 into e to the power minus 50, which is definitely less than 0.01. Cylinder 0.33, which is greater than 0.01, right? It means my cylinder is insignificant. Engine displacement 0.99, insignificant. Horsepower 0.006, guys, significant or insignificant? Everybody is saying significant? Yes, no? Good. Karina is saying insignificant. Why, Karina? Why is it insignificant? See, the value is 0.006. Is it less than or greater than 0.01? Yep, that's absolutely fine. Weight is also significant for that matter. What about accelerate, guys? Oh yeah, that's okay, Karina. That's perfectly fine. How about accelerate? No, it is insignificant. Good. So I think all of you understood how to look at this particular output and understand how the output and what the output is telling you, right? Now let's do one thing. Let's run the same model in R, okay? And I'll show you how easy it becomes to run it on R. Now, I already had one variable weight over here, right? Now I also want to add cylinders to my model. So how I do it is, all the independent variables which you want in the model should be separated by a plus sign. So do a plus sign and add the variable cylinder. I want to add engine displacement. So again a plus sign and I'll say engine dot displacement. I want to add horsepower. So again a plus sign, horse power. And I also want to add accelerate. So I'll add accelerate. So guys, I've not done anything different. I've kept the same equation. It's just that when I have multiple independent variables, then put all those independent variables in there, but separate them with a plus sign. It is as simple as that. Okay. So we'll pick up the model, run it, and then check the summary. Now, you see, we really had to look at each and every variable's p-value earlier. Okay, do I really have to look at the p-value now? It straight away tells me that which one is the significant coefficient and which are my insignificant coefficient. So if there is no star, they're obviously insignificant to me. Arvind is saying, but why is weight significant? It is greater than 0.01. Let me check. Arvind, weight p-value is 6.0 into e to the power minus 10. Look at the value. It is e to the power minus 10. Yeah. Karina is saying, but when running a multiple LM, is it mainly associated with multiple independent variables? Karina, that's the definition of multiple linear regression. Okay. In multiple linear regression, you need to have multiple independent variables. Okay. So guys, did you see how easy it became to see that whether a coefficient is significant or not? Absolutely easy. Okay, you don't have to look at what are these p-values. Just look at the stars and your job's done. Yeah. So Sridhar is asking, so does this mean we can remove the insignificant variable from the model, or is it okay to have them? Sridhar, that's a very good question. And I think I just mentioned it in the last, 10 minutes back, that if you see something being insignificant, don't remove it. Okay. And that's what we'll move on to now. Okay. Because sometimes these insignificant ones will turn out to be significant after we'll do some changes to the model. Okay. And I'll just talk about them now. But guys, is this clear to everybody till this stage? Good. What about Joshua? I can't see Joshua participating. Great. Great, Joshua. Sundaram, thanks. Great. Great. Okay. All right. So now that we have understood this piece, let me open the Word and let me explain a few concepts now. Oh, sorry. Sorry, guys. Sorry. My mic was off. I'm so sorry for that. Okay. So what I was asking is that if you guys remember, in the last lecture, we said that out of the multiple linear regression lines possible, we pick up that line where the error is minimum. Does everybody remember that? Yeah, great. This technique by which we pick up the regression line where the error is minimum, exactly, Sridhar, the one which has points closer to it, exactly, right? This technique is known as ordinary linear square techniques, OLS. Okay, so our regression model basically uses OLS technique to pick up the final regression line, and that is picked up on the basis of the fact that your error associated with that regression line is minimum. Okay, so everybody is clear on what is OLS? Yep. Why only 3 guys are clear on all these things? Hiroki, Sridhar, and Azita, Katrina also. Very nice. Great. Great. Now, guys, OLS is a technique which was, defined way back. But the person who defined OLS technique said that you can't apply this technique anywhere or everywhere. Okay. But if you really want to apply this technique to your regression model, you need to validate certain assumptions. Okay, so this guy was very clever. Okay, he said that this is the technique for regression modeling, but then he also put a caveat or a star mark which we always see saying that run it on regression model, but make sure that the assumptions which I have made are satisfied. If these assumptions are not satisfied, then your model is not good model. So whatever you have done till now will go in the vein provided you have checked for these assumptions. Even if your R square is very high, even if your ANOVA says your model is good, even if your coefficients are coming out to be significant, but if these assumptions are not validated, then there is a risk in making use of this model. Okay, then this model might not work that well. Okay, so it's very important for us to always validate the assumptions. Yes, Arvind, I'll definitely jump onto the examples. Okay, but I'm just trying to build the concept right now. Okay, yeah. So what this guy said is, given everything is fine, if my assumptions which I have assumed before building the OLS technique are not validated and they're not satisfied by your model, then your model can't be used. Or if you're using it, then use it at your own risk. Okay. Now let's see that what are these assumptions and how do we identify whether the assumptions are getting validated, and if not, then how to really change your model to validate those assumptions. Okay, so what I'm talking about is, one, you check for the assumption. If your assumption is valid, go ahead. If your assumption is not valid, okay, in that case, change your independent and dependent variable in such a fashion so that your assumptions get validated. Guys, is this clear? This is just a concept, but I hope the concept is clear that what we have to do. Not everybody. Anybody wants me to repeat it? Okay, Kaustubh wants me to repeat. Kaustubh, is this clear till the point that we are mentioning that our regression model is made out of OLS technique? Good. Now, OLS technique has certain assumptions. There are basically 4 assumptions which we will talk about. Now, what the creator of OLS technique says is that go ahead and use this technique. But if all these 4 assumptions don't get validated, whatever may be your value of R square of the model or ANOVA table or your coefficients being significant, your model is not good to be used. But if your assumptions are getting validated, then you can go ahead and use the model. That's the objective. Okay. Kaustubh, is this clear now? Good. Sorry, just give me a second, guys. Okay. Now, the first assumption of OLS is the assumption of linearity. Okay. What OLS assumes is that your dependent and independent variables will be linearly related. Okay, that there is going to be a linear relation between your dependent and independent variables. Guys, is this statement clear? Just the statement right now. Good. Now, if I have to check that whether two variables are linearly related or not, which is the best plot to go ahead with to check that? We did multiple plots, right? Okay, so Arvind and Sundaram and Hiroki and Sridhar, everybody suggesting scatter plot. Kaustubh, which plot? Yeah, Karina also saying scatter. Kaustubh, you said a plot. Which plot? Great, scatter plot. Okay, and if we look at the scatter plot, here is my independent variable, here is my dependent variable. I expect the points to be in a straight line kind of a format, right? If I'll see the points to be something like this, will this mean a linear relation if there is something like this? No, right? In that case, I would know that this is not linear. This is curvy linear, which is the wherein my assumption is not getting validated. But if let's say my dots are in a straight line, I know my assumption will get validated. Okay. So this was my first assumption. Guys, I'll take two assumptions at the same time. That's the first assumption of linearity and the second assumption of normality. Okay, and then I'll showcase it to you on how to check this on R and how to transform your data so as to get them validated. Okay, so let's look at linearity and normality first. I hope everybody is clear on what is the assumption of linearity. Yes, great, great. Okay, now let's now move on to the assumption of normality. Anybody remembered error term? What was the error term? I talked about it in the last class. Error term. Guys, yes, no? Anybody remember? Sheila says difference between the point and the line of regression. Exactly, Sridhar. Very good. Wonderful. Hiroki says residual. Wonderful, Hiroki. Perfect. 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 Guys, if I have to explain it to a layman, I'll call the error term as the difference between the predicted value and the actual value. Okay, so for example, if the weight of car is 2000 kgs, okay, and we know that the mileage it is giving is 18 miles per gallon, okay, but when I ran a prediction model, when I ran a regression model, I found the predicted value to be 15. Then this 18 minus 15, that's 3, is my error. Clear? Everybody? Okay. The second assumption of normality says that you calculate the error term for each of your data point, and these should be normally distributed. How they should be? Normally distributed. Okay. How does a normal distribution look like, guys? Remember from the first lecture, what is the shape of normal distribution? Bell curve, exactly. So your error terms should be normally distributed. Okay, so if they are normally distributed, your assumption is valid. If they are not normally distributed, then your assumption is not valid. Guys, is the statement of normality clear to everybody? What is normality? So Sridhar, error terms of each and every data point, yes, you take all of them together and all of them together should form a normal distribution. Yeah, great, great. So guys, the first assumption was the assumption of linearity. The second assumption was the assumption of normality. Okay, now let's see how to check for these assumptions in R. Okay, and in parallel, we'll also try and find out that if these assumptions are not met and if they are not valid for our model, then how to correct these assumptions. Okay. All right. So let me quickly move on to R. Guys, I would request you all to please first look at the process which I'm running you through. Okay. And once we have run through this process is when you should ask questions. Okay, because there is a proper flow to it and a lot of your questions will get answered while we'll run through this flow. Okay, so I'm opening an R code which is already there with you guys on LMS, that R code linearity and normality. Okay, so you can always download it from LMS and refer to it whenever you want to. Now let me just clean all the variables. All right, so guys, let me quickly run and load the data set again. Okay, so I have my A variable now. Okay, now let's say I want to run a simple linear regression model between the miles per gallon and the horsepower. Okay, so guys, how will I check the assumption of linearity? How will I check the assumption of linearity, guys? Scatter plot between the two variables, right? So my first variable is horsepower and the second variable is miles per gallon. Now, if you'll remember from our basic, our basics class, we said that for a scatter plot, you first need to provide the x-axis and then the y-axis. So horsepower in this case will be your x-axis and actual MPG will be your y-axis. Okay, so let me run this plot and see that how my plot really turns out. So guys, what do you say? Is this a linear relationship? Tell me guys, does this look linear? Yes, Hiroki, it's a negative relationship, but does it look linear or it looks curved? Curved. So if I'll run a model with this kind of a data, will my assumption get validated or will get rejected? Not good. Okay, but let me still go ahead and run the model. Let me still go ahead and run the model and check the output. Guys, what is the R square value over here? How much is the R square? I'm sorry guys, I think I got muted again. There is some issue. But okay, what I was saying is that if you look at the model, it did a decent job. Okay, my R square is 60%. My coefficients are significant. My model is significant, but my linearity assumption is not validated. So I can't rely on this particular model. Okay, and the next thing for me to check is the normality. And how do I check normality? By checking that whether my residuals are normally distributed or not, right? And how to do that? So Sridhar says do a histogram. Arvind says distribution chart or histogram. Okay, that's a very good attempt, guys, but there is a much simpler way to do it. Okay, you might get confused looking at a histogram in a scenario when you have two peaks. What will you do? If you'll have two peaks, will you say that your model is normal or not? You'll get confused, right? Okay, so there is another plot which is very commonly used to check the normality of any data, and that plot is your QQ plot. That plot is your QQ plot. Okay, now let me show you how to make use of that plot. Okay, now before I really show you that plot, let me show you what all your model has to offer. So we looked at the output of the model and we found out the intercept coefficient, the horsepower coefficient, the R square and everything. The model automatically calculates the residuals for you. Okay, it does that calculation automatically. So it picks up the coefficient values, find out the predicted value for each and every data point, subtract it from the actual value and calculate these residuals automatically for you. So these residuals are readily available for you when you're running a model. Okay, and the way to access these residuals is exactly the way you access any variable in your data set. So you do model one, which is the name of our model, dollar residuals. So the moment you run this, ouch, what happened? Is there something wrong? Guys, I think my R has hanged. Let me just restart it again. Let me just restart it again. Okay, I'll not save it. I don't know why it got hanged. No, Kaustav, attach is not required, but I think my R is not functioning right now. Let me just close it. Don't save. Let it just quit first. Something wrong with my R. Yep. Let me reopen my code for linearity and normality. Okay, and let me just load the data set again. So I'll load the data set. I obviously checked for my linearity assumption, which wasn't validated. I ran the model, I summarized the model. Okay. And I was saying that if you have to check, the residuals, you can do it using model one dollar residuals. Okay. So it automatically gives you the residuals. So if you'll see, you'll realize that for each and every data point, so the first data point, the residual was 5. The second, the residual was -4. Okay. So it over predicted, under predicted kind of a scenario. Okay. Now, what you can do is you can do a QQ plot. Remember, I was saying that the QQ plot is the way to check the normality of any data. So you check the normality of residuals by giving the residuals to your QQ plot function. Okay, so you do that. Ouch. It could not find function QQ plot. Ow. Sorry guys, just give me 1 second. I'm not sure why it is behaving weird. Yeah, here it is. Okay, so guys, basically what happened is that this QQ plot function is available in car package. Okay, so this is the package which you obviously have to install before you get this function. And once you have installed it, you run this function QQ plot and you get to see a plot like this. Okay, now don't get scared of this plot. It is a very simple plot. If, okay, these dots which you're seeing over here are your data points. Okay, now what QQ plot says is that if these data points are aligned to this central state line, it means your data is normally distributed. If they are not aligned to this central state line, then your data is not normally distributed. Okay, so when we ran the QQ plot on the residuals, we got this kind of a plot. Now tell me, if my data points are normally distributed, is my residual normally distributed? Guys, is my are you sure it is normally distributed? Can't you see these points out here going away from my central line? Yeah, exactly, Sridhar. So even if they are away from the central line, they should lie within these dotted line bounds. So over here, these are within the dotted line bounds, but over here they've gone ahead of the dotted line bounds. Okay. Yes, very few, but our target is always to make as many of them to come within this range as possible. Yeah, I can definitely zoom the plot for you, Kaustubh. That's not a problem. Now, can you see it better? Yeah. Can you see that most of the points are within the range, but over here, a lot of points are going out of the bounds. Okay. So we are very closer to the normality assumption, but not yet there. Okay. We can improve on this. Yeah. So this is not very bad output. Okay. But it is still not there. We have to improve upon it. That's the point. Okay. Now, how to do this improvement? The way to do that is by means of data transformations. Okay. Now, let me explain that piece to all of you. So guys, whenever we see that an assumption is not validated, okay, it is getting rejected. Okay, in that case, you have to transform your independent or dependent variables. Okay, now when I say transform, you have to do some mathematical operation on these variables so that they start following your assumptions. Okay, a few of the very commonly used mathematical operations are log function, square function, square root function, okay, and cube function. Okay, so depending upon how your data is behaving, you apply one of these functions to make your data follow your assumptions. Okay, now let me quickly show it to you with an example and it'll become much more clearer. Let's go to our R studio only. And let me fix the first assumption of linearity here. Okay, now if you look at the linear plot, you guys could very clearly see that there was a curve out here, right? Okay, now if I have to fix it, what I did is I did a log transformation. All the horsepower values, I took a log of all the horsepower values. Okay, so that's one transformation I did. Ouch, sorry. I did one transformation and I converted the horsepower value into log of horsepower value. And now let's look at the plot of horsepower versus actual MPG. Guys, does this look a little better? Does this look a little more linear? Yeah? Everybody? Right? So guys, by doing a simple log transformation, I could correct one of my assumptions of linearity. Okay, and since my linearity assumption got corrected after transforming the variable to a log variable, I should use the, okay, Arvind is saying, I'm sorry to ask, but what do you mean by log transformation? Arvind, the original value of horsepower is now changed to log value of horsepower. So if earlier the value was 10, now the value is log of 10. Okay, does this make sense? Not okay. What exactly are you not okay with, Arvind? Arvind, your question, please. Log value. Okay, so what is not clear of the log value? What I'm trying to say is, when your data was not linear, okay, we had to apply some transformation to your data so that it starts looking linear. Okay, and we tested and found out that log is the one of the methods to use over here. So if you'll log convert your variable, if you'll transform your variable by converting into a log form, your data will start looking linear. This is just one way of modifying your data. Okay. Exactly, Kaustubh. The logic here is simple mathematical modification, nothing else. Okay, let's say if I would have used a square transformation, what would have happened? So let's say if I would have done this, rather than doing a log, if I would have done a square, let's say, okay, so I'm doing a square of horsepower, and now let's see how does it look. The moment I did a square, it became much more curved. right guys? So the square transformation is not helping me out here, right? What if I would have done a square root? If I would have done a square root, let's say, and then I would have plotted. Almost there, but at the end, I can still see some curve. Guys, can you see this? There's still a little bit curve. Yeah, but the moment I did a log transformation, I could see my plot being almost linear. Okay, you want me to use cube? I can do that too. Let's use cube. See, I used cube, but there is still a little bit of a curve out there, right? So which was the best transformation for us? Log transformation. Okay, so when we did the log transformation on our data, our problem of linearity, so when our assumption of linearity got validated, okay, and now when I'll run the model and see my results, now guys, can you see the results over here? What is my R square now? Guys, what is my R square now? It improved, right? Yes, earlier it was just 60%, but the moment my transformation validated one of the assumptions, my model improved to close to 67%, right? So guys, this is one of the proofs which tells you that as you start becoming closer to your assumptions, as you start validating your assumption, there is a high probability of your model also to improve. Okay, and now let's see that once we have done this transformation, how our QQ plot looks like. Are the residuals becoming a little better? So when I run the QQ plot, see, let me just zoom it for all of you. Now, if you look at the QQ plot, a few of the values have started becoming better, right? So one small transformation helped me in correcting my linearity and a little bit of normality also. But are we still there? There is still some problem, right? There's still a very little problem. Can we correct this? So let's see if we can correct it. Okay. Let's see if we can correct it. Till now, I only log transformed my independent variable. Now let me do a log transformation of my dependent variable also. Okay, so I'm log transforming my miles per gallon too. And now when I check the plot, wow. So guys, let's do a quick comparison. This is one plot where in both my miles per gallon and horsepower are log transformed. Whereas this is another plot wherein only, if you look at the last plot, where is that? This was the plot where only my horsepower was log transformed. So this is where only horsepower is log transformed. This is where both horsepower and miles per gallon are log transformed. Which is better? Which is better? Both log transformed. Exactly. Exactly. Yeah. Sridhar, yes, there is a way to do that. So Sridhar is asking, is there a way we can plot both the plots side by side? Yes, there is a way, Sridhar. I want you to figure it out. Okay, I would want you guys to figure that way out. Okay, yeah, all right. So now my linearity has become much more clearer. Okay, and now let's run the data, run the model, sorry. So when I run the model now and look at the output, guys, what is my R square now? When I didn't do any transformation, what was my R square? And now it is 72. So once you got closer to your assumptions, your predictability also improved, right? And now let's check our QQ plot again. So if you look at the QQ plot of residuals, ouch, what happened? Did I do something wrong? I ran the model, I did the summary of model, then I ran the QQ plot. Yeah, here's the QQ plot. And now let's zoom it. Guys, QQ plot, how does it look? Arvind is saying further improved. Arvind, all improved. Everything is there now. Guys, understood? So when somebody created that OLS technique, they very carefully also wrote the assumptions which one should validate. Okay, and these were the first two assumptions. Is everybody clear on these assumptions? Great, good guys. So there are two more assumptions which we have to go through. Okay, and we'll do them after our break. It's 9 o'clock. Let's take a quick 15 minutes break and let's come back and we'll validate the rest two assumptions also. And once we are done with those is where we'll start with the logistic regression. Okay, so guys, uh, okay, first of all, Kavitek, my name is Ujwal, and yes, it's kind of a trial and error methodology, okay, wherein you have to see that what kind of transformation is required by the data. Now, while I have already played with this data set a lot, I know that what kind of transformations are required, and that's how I have straight away put those transformations in there. Okay, but yes, this requires a lot of practice. The moment you'll start visualizing data and the moment you'll start plotting data, you yourself will start understanding that what kind of transformation is required. This trial and error will become much more easier going forward. Okay, so guys, let's take a quick 15 minutes break. I'll catch you guys after 15 minutes. It's 9:03 by my watch. Let's catch up at 9:15. uh, Cost log transformation is most commonly used. Okay, but there are a lot of other transformations. We have anyway shared a document on transformations with you. Okay, but you can always go ahead and read it on net. Okay, great. Let's catch up in 15 minutes, guys. Thank you. Not a problem, Kavitak. If you're not watching rest of the class, please go ahead and watch the videos and you'll understand it. Not a problem. Thanks. Hi guys, hope everybody's back. If yes, can you please quickly type it in the chat box? Good, 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 good. Everybody's back. I was the one who was late. Sorry for that. Okay. So guys, we looked at the two assumptions of normality and linearity. Okay. Now we'll move on to the next assumption. That's the assumption of heteroscedasticity. All right. Heteroscedasticity, and let's just understand what exactly heteroscedasticity means. Okay, so they're basically two terms over here. Guys, they're basically two terms. Okay, first of all, don't get worried with the name. I know the name is a little bigger, but it's a very simple thing to understand. Homoscedasticity and heteroscedasticity. Okay, now what the assumption of OLS says is that your residuals, everybody remember residuals? Error terms? Yeah, yeah. Your residuals should be randomly distributed. There should not be any relation between your residuals and your predicted value. So there should not be any relation between your residual and predicted value. If that is the case, then you can call your residuals being homoscedastic and your assumption is met. But if you see some relation between your residual and predicted value, then your residuals are heteroscedastic, okay, and your assumption is not met. Okay, guys, is this clear? Is the statement clear? Exactly, Sridhar. So when you will draw a plot between your predicted value and your residual, you should see a random plot. You should not see a straight line or a curve or any kind of a relationship in there. Yeah, you should see all the dots being very randomly, scattered. That is the expectation. Okay, guys, is this clear to everybody? That what is homoscedasticity and what is heteroscedasticity? Great. Now let's try and see that how do we really validate this assumption. Okay, Sridhar wants me to repeat this once. I'll do that, Sridhar. Yeah, very quickly. What we are trying to say is that you have residuals, right? And you also have predicted values for all your data points. What this assumption says is that there should not be any relationship between these two. Okay, so for example, if let's say you have predicted residuals and your predicted value, yeah, let's say the plot turns out to be something like this. Can I say that there is a relationship? Guys, can I say that there is a relationship in here? Kaustubh, there is a relationship. Not linear, but curvilinear. There is a relationship. Okay. But let's say if the plot turns out to be something like this. Can you see any relationship between the X and Y axis over here? Is there any relationship which you can make out? No. This is the expectation from a residual versus predicted value plot. Okay. So if your model is giving an output like this, You can say your model is homoscedastic and everything is fine. Okay, your assumption is validated. But if your model gives the residual versus predicted value plot something like this, then there is a problem and some kind of data transformation is required to correct that plot. Okay, great. Now let's go to R and see how do we do it. Okay, so yeah, here we are. Again, I'm doing nothing but reading the same cars.csv file. Okay, now since this file has a lot of categorical data also, like origin is, you know, American European, year is there, then you have model names. I don't want to use these in my model. So what I'm doing is I'm just selecting only those variables which are numerical in nature. Okay, so as you can see that now I have picked up only the numerical values. Now let's check these plots. Okay, so obviously we had to, you know, look at the plot of each of these variables with the dependent variable to see if linearity can be found out. So cylinder, a plot which I can't comment on, you know, because this is more of a discrete variable. You know, the plot doesn't look really interesting. But let's look at the engine displacement. Guys, is linearity validated? Is the linear assumption validated in this? Is there a linear assumption validated? Does this relationship look linear? No, it doesn't. It's a little curved. Exactly. Okay, so there is a problem of linearity also. But in this case, we are not focusing on linearity. We'll focus more on heteroscedasticity. Okay. Now let's check horsepower. Again, doesn't look that linear. Let's check the weight. Again, doesn't look linear. Let's check accelerate. Don't know. Can't comment. Can you comment on this plot? Whether it is linear, not linear, or what it is? Do we know? Can we make out anything out of this plot? Nah, I can't comment on this plot. We don't know. Yeah, exactly. We can't really give any relationship out here. Okay. So let's still go ahead and run our model, the first model, and see how the output looks like. So I ran the model and I run a summary. Guys, what is my multiple R square? What is my R square value in this case? 81%. Wow. That's some level of prediction, right? So if somebody who would have not known about the assumptions would have run this model, he should have become very happy saying that my model is predicting 80% correctly. Okay, and it would have gone ahead and used the model. But now that we know the assumptions exist, will you really go ahead and use the model as it is? Will you go ahead and do it? No, not yet. You first validate all the assumptions. Okay, Sridhar has a doubt. Sridhar, tell me what's the doubt? The formula use. Which formula? Sorry, Sridhar, can you point me to the formula? Which formula you're talking about? LM formula. Okay. Yes. Ah, right. Okay, that's a good pick. Very good, Sridhar. Let me just explain that. I understood your question. Guys, if you'll see over here, we have this tilde, but after that, we didn't mention any of the variable names. We mentioned a dot, right? Now, guys, I think I'm sorry for this miss. I should have told this to you earlier. In case you want to use all the independent variables from your data set, okay, then you don't have to write the names individually. just put a dot over there, and R will understand that rest all the variables apart from the dependent variable has to be used as independent variables. I hope I'm making it clear. I hope it is clear to everybody. Yeah, great. So next time when you have yes, Sundaram. So I have initially only I have reduced my data set to all the numerical variables. So that's how it'll pick up all the numerical variables. So going forward, let's say if you have a data set from where you want to pick up all the variables, you don't have to go ahead and write the name of these variables. Just put a dot over there and R will do the job for you. Okay, great. Now, you remember I said that for heteroscedasticity, you have to see the value of your residuals versus your predicted value. Now, the way your model gives the value of residuals automatically, it also gives you the values of your predicted value. Okay, so if you do model $1, you'll see over here fitted values. These are nothing but all the values which model has predicted for you using the formula which it has used for. So for the first data set, first data point, it predicted the miles per gallon as 13. For the second, it predicted the miles per gallon as 21, and so on and so forth. Okay, so both these values are available with us from the model itself. And now let's plot this model and plot these two values: fitted value, which is going to be your x-axis, residuals, which are going to be your y-axis. Okay, guys. So tell me, do you see a relationship between residuals and fitted value or not? So Arvind still says there is no relation. Azita says no relation. Sundaram says no relation. Guys, are you sure there is no relation? Not really, says Karina. Can you see some kind of a curve in there? Yeah. It means definitely, yes, it is scattered, but is it randomly scattered is the question. Our expectation is that these should be completely randomly scattered. Are these randomly scattered? No, right? You can see a downfall first and then the upscaling happening. So this is not a random scatter. A random scatter, in a random scatter, you should not be able to see any kind of a curve or a pattern, but there is a pattern which you can see, which means your assumption of homoscedasticity is not validated and your residuals are heteroscedastic right now. Okay, guys, clear to everybody till this point? Good. Now, once you know that there is heteroscedasticity, okay, obviously you have to do some data transformation. Now, how do we know on which variable the transformation is required? Okay, in order to find that out, you plot your residuals against each of the independent variable. Okay, so that's what we'll try and do next. So guys, as first step, we plotted our residuals against the fitted values. Okay, and now since we have seen that there is a relationship, we want to find out that because of which variable this relationship is coming out. And to find that out, we are plotting residuals against each of the independent variables. Okay, so let's do that. So I first did a plot of residuals for cylinders. Again, can't find out anything much about cylinders. It's a discrete variable. I'm not able to gain any information. Let's look at engine displacement. So residuals have some kind of a relationship over here with engine displacement. Guys, Can you see this? That there is some kind of a curve over here also. Yeah, exactly. So engine displacement could be one culprit, which is leading to heteroscedasticity. Now let's check horsepower. Um, I can't say that there is a lot of heteroscedasticity because of horsepower, but still there is some kind of a relationship which I can very well see. A blurred curve, exactly, Sridhar. A very blurred curve. So we might have to take horsepower also into consideration. Now let's look at the weight. Yeah, here I definitely have I can definitely see a curve over here, right? Yes. And then let's finally look at the accelerate. Hmm. Any relationship, guys? Random. Yes, this is random, guys. This is completely random. Yeah. Rest all had some kind of a relationship. This is completely random. Okay. So now that we know that there is some kind of a relationship which is there for engine displacement, horsepower, and weight, let's just do some transformations. So again, I'm doing log transformation on all four of them. I'm doing log transformation because I've already tested it for all the other transformations. Okay, guys, since I've tested it for all the other transformations, uh, guys, is everybody else able to hear me? Yeah, okay. Okay, so what I'm saying is that since I have tested all the other transformations, I found that log transformation is the right one to go ahead with. Okay, and that's how I'm just doing log transformation on all the three independent variables and also on my dependent variable. Okay, and I ran the model again. And now let's see that what my model has to offer. What is the output? Guys, what is the R square now of the model? What was the original R square? No, it was not 60. 60 was when we were doing the previous model. In this model, the original R square was 81%. So you see an improvement of close to 7 to 8%. Yeah. Another point to notice, if you look at the first model we ran, which all variables were turning out to be significant for us, guys? Which all variables were significant in the initial model? Weight, okay, and year, and our intercept. No, accelerate was not, guys. Accelerate was not. Yeah, weight, intercept, and years. But after I did the transformations, how many variables are now coming out to be significant? Which all? Now you have intercept, you have horsepower, weight, accelerate, year, all of them becoming significant for us. Yeah. So you see that earlier there were certain variables which were not significant, but after I did the transformation, I could see them being significant. And that's where I said that in the initial run, if you see a variable being insignificant, don't throw it out of the model. Throw it out of the model, but only when you have checked all the assumptions and made them valid. Because a few of these variables might become significant later. Yeah, great, great. And now that I have run this new model, now let's again check my fitted value versus residual to check if there is any sort of heteroscedasticity. Yes, guys. So is it random or is it having some relationship? Will you call this random or will you call the last one random? This one, right? So my model has become homoscedastic now. And if you'll check the plot for rest of the independent variables also, I'm sorry, not cylinder, engine displacement. Earlier it was showing some kind of a curve. Now it has become completely random. Horsepower, completely random. Weight has become completely random. Accelerate was anyways random. Yeah. So you see, once we corrected our assumption of heteroscedasticity, our model became, absolutely okay. Guys, is this clear to everybody or anybody has any questions? Arvind has a question. Please, Arvind, tell me. Oh, Arvind said clear. Okay. Sorry. Okay. Hiroki is asking, so after checking, we can drop insignificant variables. Yes, Hiroki, once all the four assumptions are validated, then all those variables which are not significant can be dropped out of your equation. Okay, great. Okay, so guys, till this point, what we have learned are three assumptions of OLS modeling. First, the assumption of linearity, the assumption of normality, and the assumption of homoscedasticity. I'm not writing, that's a big word. Okay, so these are the three assumptions which we checked. The fourth and yet another important assumption is the assumption of collinearity, or people call it as multicollinearity. Okay, now guys, before I show you how to check this particular assumption, let's understand that what this assumption is all about. First and foremost, the assumption of multicollinearity applies only to multiple regression models. Okay, that's the first condition. You don't have to check for this assumption when you're running a simple linear regression. When you're running a simple linear regression, you don't have to worry about this assumption. But if you're running a multiple linear regression, is where you have to worry about this particular assumption. Okay. Now what this assumption says is that none of your independent variables should be correlated to each other. Okay, so what it says is that none of your independent variables, okay, they should not be correlated at all to each other. Okay, so for example, let's say I run a model to predict the sales of a company on the basis of advertisement expenses and manpower, and let's say number of advertisements in the newspaper. Now tell me one thing, don't you think if my advertisement expense will go up, my number of advertisements will also go up? Guys, what do you say? Yeah, in which case, can I say that my advertisement expense and number of advertisements are correlated to each other? Can I say that? Yeah. So that's what your OLS assumption says, that in this kind of a scenario, your model can't be trusted because there is a correlation between your independent and dependent, two independent variables, sorry. Okay, so there is a relationship which is existing between your independent variables. They're collinear. There's a dependency. Exactly, guys. Okay, and what should I do in case I find out that two variables are collinear or they are related to each other? What should we do? Exactly. Drop one of them. If you'll drop one of them, then there'll be no correlation. Your multicollinearity will get solved. Okay. Thanks a lot for that answer, Hiroki. But let me ask another question on top of that. Which variable should I drop? Number ADV. Okay. Why, Hiroki? Why number of advertisements should be dropped? Sridhar says the one which is less collinear. No, no, guys. Okay, there is nothing like less collinear or more collinear. If these two have a correlation of zero 0.8, then there is a correlation of 0.8 between these two. Both of them are like 0.8 collinear, right? Yeah. So you can't say that there is less collinearity or more collinearity. So which variable should I drop? Any other guesses by anybody? Do trial and error. Um, Kind of, but a logical trial and error. A logical trial and error. Hiroki is saying that you should drop number of advertisements because money will have more impact on sales. Uh, Hiroki, yeah, subjectively I would agree to you, but there is an objective way to find things out. Yes, so I think Sridhar is coming closer to the answer. The one which is less related to the dependent variable. Guys, exactly. Think of it from the perspective of dependent variable also. Yeah. If my advertisement is having more impact on predicting sales as compared to number of advertisement, I'll definitely drop number of advertisement. But what if my number of advertisements have more impact on finding sales as compared to advertisement? Then I'll drop advertisement expense and keep number of advertisements. Yeah. So Hiroki, you were very close to the answer, but objectively you have to find out that which is more, you know, supportive in predicting sales. Yeah. Guys, is this clear to everybody? Exactly, Hiroki. It depends on the impact. And now let me ask my last question. How do you calculate impact in regression modeling? How do you calculate impact on in regression modeling? There is something which we are very clearly aware of. Very nice, Kaustubh. R square. R square tells us that how much of an independent variable is helping me predict my dependent variable. Remember, guys, my predictability. Yeah. So what I'll do is, in my multiple regression model, if let's say I'm predicting sales on the basis of advertisement expense, number of advertisement, and sales force, and I find out that these two are multicollinear, what I'll do is I'll run a simple linear regression on sales for number of advertisements and sales for advertisement expense, and I'll check the R square for both of them. Wherever the R square turns out to be higher, I'll pick that variable up. Exactly. Guys, is this process clear to everybody? I can see only 3 or 4 of the participants really participating. What about others? Joshua? Okay, Arvind wants me to explain once again. Okay, what I'm trying to say is, guys, good. I didn't get a response from Joshua, that's why I took your name. Was this clear to you? Okay, you run a multiple regression. Y is equal to m1 x1 plus m2 x2 plus m3 x3 plus c. You find out that x1 and x3 are collinear. They have a correlation between them. So in order to find out that which one to drop, you run a simple linear regression of y is equal to mx1 plus c and y is equal to mx3 plus c. Wherever the R square comes higher, keep that variable in your model and reject the other one. Arvind, is it clear now? Exactly, Hiroki. Once you'll do the multiple linear regression, then in order to find out that which variable to drop, you'll run two separate simple linear regressions and then pick up the variable which is giving you more R square to clear your multicollinearity. Yep. Clear to everybody? Karina? Yes, I completely understand that. You might have to, but please make sure that you repeat the class. Yeah. And it'll become clearer. Okay. So let's run, a simple example of multicollinearity. Okay, so guys, for this particular example, I have taken a different data set. Let me quickly show that data set to you guys so that it becomes clearer. Where is the data set? Linear regression version 1. Yeah. Okay, so guys, this data is of a claims, is of an insurance company, okay, wherein you have policy numbers, age of the policy holder, the number of years of driving experience this policy holder has, number of vehicles this guy holds, the gender of the person, whether the person is married or unmarried, what is the age of the vehicle, whether the person uses a diesel run or a petrol run car, and how much was the claim this guy has lodged for this particular vehicle. Okay, and our problem statement is to predict that how much of a claim will this guy lodge for given these attributes of the policy. Okay, so everybody understood the problem statement? Yeah, we have to predict the claimed amount given the attributes of the policy, and the attributes being the age of the driver, years of driver experience, and XYZ. All these attributes are there. Okay, so I'm making use of this particular data set for showing you that how to find out multicollinearity. Okay, so let me quickly run and get the data in there. I have to pick up the folder path again. Yep, it's fine now. Now let me quickly read the data. This is the data over here. Okay. And guys, since I'm not running the model on all the variables, I have given the name of all these variables over here. Okay. So I have run the model and I can see the summary of the model. So as you can see that my model is pretty good, 75% R square. Okay. And it has a lot of variables which are significant out here. Okay. But now we have to check for multicollinearity. Okay, so guys, there are two ways in which you can check the multicollinearity. Let me tell you those two ways. One, you check the correlation value between every pair of independent variable. Yeah, this is fairly simple, right? You check the correlation value between every pair of independent variable. So if you'll see the value being a high positive or a high negative value, you know that there is a correlation which exists. Another way to do it is by finding out a value which we call as VIF. That's variance inflation factor. Okay. You find out the variance inflation factor for all the variables of your initial model. Okay. And if the VIF value for the independent variable is more than 2, is where you know that that particular variable is multicollinear with some other variable. Yes guys, let me repeat that again. If you know that the VIF value found out for all the independent variables, for any of these variables, if the value is greater than 2, then you know that this particular variable is having a multicollinearity problem. Okay, so the way to identify multicollinearity, there are two ways. One, you find out the correlation between each and every variable pair. Second, you try and find out the value of VIF, okay, for all the variables. And if the VIF value is greater than 2, then you know that there is a problem in these variables. Okay, so let's find out the VIF value. So I run the VIF value, and as you can see over here, that for all the independent variables, my years of driving experience and average age are the two variables where the VIF value is greater than 2. And guys, is it not sounding logical also that if the age of a person is higher, there is a very high probability that the years of driving experience are also going to be higher? Yeah. And that's why there is a possibility that both of these variables are collinear with each other. There is a correlation existing between these two variables. Okay. So what will we do? We'll run a simple linear regression model for each of these variables, check their R square and remove the one where the R square is going to be lesser. So I'll run the first model wherein I'm trying to predict the cap losses on the basis of average age. I run the second model wherein I'm trying to predict the value of cap losses on the basis of driver's experience. Once I've done that, let's check the summary of the average age variable. Guys, what is the R square in there? 26%. And for years of driving experience, what is the R square, guys? 19%. So which variable will we keep in the model? Average age. And we'll drop the one where we have the R square as 19 or 20%. That is years of driving experience is what we will drop. Okay. So if you look at this particular new model which I'm about to run, I have the average age, but I have removed years of driving experience from here. Okay. So let me just run this. And now when you look at the VIF value, all the VIF values are less than 2. Can you see that? So our problem of multicollinearity got resolved. Okay. And now let's run the summary of this model again. So you see, my R square is still very 75-ish type. And our final model is this. Now, as you can see that number of vehicles is not making sense. It is not significant. You can go ahead and, remove this variable also if you want. Okay. Provided you have checked for the other assumptions also. Yeah. So guys, are these assumptions clear to everybody? Good. Now guys, let me caution you a little. Over here, these might have sounded very easy because we use the transformation straight away in a lot of variables. Okay. In real life problems, these things are not going to be that easy. Okay. And you'll end up doing or end up testing a lot of transformations, after which you will really end up finding out that what needs to be done. Okay. So what is required is a lot of practice. I'm giving one data set to you guys as homework. Okay. The name of the data set is climate change. Let me tell you what this data set is. This data set tells you the composition of, composition of air surrounding you in terms of carbon dioxide, carbon monoxide, nitrogen dioxide, CFCs, etc., etc. And you're expected to predict the temperature of that particular day. Okay. So all these are your independent variables and temperature is your dependent variable. Now what I want you guys to do is, I want you guys to go back after the class and make sure that you practice and run a regression model on this particular data set. Yeah, will everybody do it? But guys, this is just one data set. You might find a lot of challenges coming in here. Try and figure them out. But I also want you to use your best friend, Google, to find out as many data sets as you can and run regression model on top of it. Yeah. Okay. Please make sure you do it, because if you will not, then all this exercise will go in vain. All that we have studied today, you'll definitely forget by tomorrow. I think Sridhar has shared something with us. Thanks a lot, Sridhar. So Data World is what Sridhar is saying is a website which gives you a lot of data sets. Okay. So guys, this is where we end the topic of linear regression. Everybody is clear on this topic? Yeah. Great. Great. Okay. Okay. Joshua, a guess is okay, but I would want you to practice, please. Sridhar, thanks a lot for sharing this link. Yes, everybody needs to practice a lot. So guys, now that we have understood linear regression, let's get started a little on the next topic. Azita is saying, once we are done with all that we did, what is the final output and how will that be submitted? Oh, okay. So guys, can you hear me? Karina, you might have to check at your end, because I think I should be audible. And to answer Azita's question, Azita, the final output will be, yeah, I think Karina, it is just you. Everybody else is able to hear me. Okay. And to answer Azita's question, Azita, the final output has to be in the form of this. This is simple linear regression. This is multiple linear regression. So once you have done all of this, you'll ultimately find out that a few variables will be significant and a few variables will be insignificant. After you have tested all your assumptions and everything is now perfect, remove all the variables which are insignificant and create a final equation with the significant variables. Okay, and using the equation which you'll make, you'll be able to predict the values of y given the values of x1, x2, x3 and so on. Yeah, great. Okay, all right, so what I was saying is, let's get started with the next topic. Logistic regression. Yeah. Before I get started with that, guys, tell me one thing. What was the type of variable which we were trying to predict using linear regression? Numeric, okay. Can I say continuous? Yeah. So in case of linear regression, we were trying to predict a numerical outcome. Okay. So these kind of problem statements are very common. You know, for example, somebody will ask you, how much will I sell next month? Or somebody will tell you, how much will I get as salary in next month? You know, how much hike will I get next month? All these kind of problems can be answered through linear regression. What if the problem statement is like this? Tell me that whether Joshua will attend tomorrow's lecture or not. What kind of an outcome is this, guys? Yes or no? Can I say it as a binary outcome? Yeah. What if the problem statement is that Ujjwal has taken a loan from HDFC, whether he will default on the loan or not? What kind of an outcome is this? Binary again, right? Whenever we have a problem statement where the output or the outcome is expected to be binary in nature, in the form of yes or no, in the form of true or false, in the form of 1 or 0, for such outcomes we use logistic regression. Guys, clear of the scenario where we use logistic regression? Yeah. Joshua is not clear. Tell me, Joshua, why is it not clear? Okay, you want me to repeat? Not a problem. Joshua, whenever we expect the outcome or the result to be of a form of true or false, yes or no, 1 or 0 types, whenever the outcome is binary in nature, linear regression is not the right model to go ahead with. You should use logistic regression technique. Is this clear now? Yes. Okay. Now, why can't I use a linear regression? Why is linear regression is not good? So let's say I want to find out that whether somebody will come in tomorrow's class or not. So if somebody comes into the class, the outcome is 1. If somebody doesn't come to the class, the output is 0. This is also numeric. So I have converted your binary to numeric numbers. Now why can't I use a linear regression? These two are numbers, right? Guys, any clue? No? Yes? Guys, any clue? Yes, Sridhar, they were categorical, but now I converted them to numbers, na? 1 or 0. They imply a category, true. But can't I predict a 1 or a 0? The outcome, the output can be 1 or a 0, right? Okay, the reason is not that. The reason is not that. Let me tell you the reason. What was the equation of linear regression? Right? Now let's say my x turns out to be very big. 10,000. And let's say my M value is 2 and my C is 30. What will be the value of Y? 20,000 plus 30, that's equal to 20,030. This is the value of Y. Now, will you term Y as 1 or 0? What will you term it as? Can't say, right? Can we say it? No. Because the value of linear regression output can range from minus infinity to plus infinity. Okay? I can't use linear regression to find the outcome as 0 or 1. Okay? And that is where your logistic function comes into play. The formula for logistic function is something like this. The probability of Y happening is equal to 1 divided by 1 plus e to the power minus z. Z being some variable. Okay. So guys, again, the formula for logistic regression is probability of an event happening. In our case, let's say we talk about a student attending a class. So probability a student attending a class is equal to 1 divided by 1 plus e to the power minus z. Okay. Now let's say I replace this z, okay, with an equation, which is something like this. Z is equal to mx plus c. Right? Now tell me one thing. What range can z lie in? As I just said, z can lie from. In what range can z lie? Minus infinity to plus infinity, right? Now howsoever big value of x is going to be, let's say my z value is minus infinity. So what will this value turn out to be? It will be 1 divided by 1 plus e to the power minus of minus infinity, right? That's equal to 1 divided by 1 plus e to the power infinity, and that is equal to, Sridhar, are you sure it will be 1? 0. 1 divided by infinity is 0. Now let's assume that the value of z turns out to be plus infinity. Then my equation will be 1 by 1 plus e to the power minus infinity, and the ultimate value will turn out to be 1. So for my logistic regression equation, the value lies between 0 to 1, which is nothing but the range of probability. Okay, so the outcome of your logistic regression equation is the probability of an event happening. Now I can always define a threshold. So let's say I say that if the probability is more than 0.6, then I'll assume the event happening. Exactly, Kaustubh. The equation made the range change from infinity to 0 to 1. And now since I have the probability that is between 0 and 1, I can always define a threshold. For example, I can say that if the probability of event happening goes more than 0.6, I'll assume the event happening. If it goes less than 0.6, I'll assume the event not happening. Right? Or you can say that I can define my probability as 0.3. If anything goes beyond 0.3, I'll assume the event happening, else I'll assume the event not happening. Guys, clear why are we using logistic regression and how do we use it in our model? To everybody? Good, good, very nice. So again, just to reiterate, the way we'll run a logistic regression model is you will first find out the probability of y. That's going to be from the equation 1 by 1 plus e to the power minus z, where z is going to be nothing but of the form of z is equal to mx plus c. Once you have this value in there, we'll key that value in here. Okay. And once we'll key that value in there, we'll find out the probability. Now this probability has to be compared to a threshold value. If the probability is more than the threshold, we'll assume that the event will happen. That's 1. If the probability is less than the threshold, we'll assume that the event will not happen. That's 0. More than threshold, yes, true, 1. Less than threshold, no, false, 0. And defining this threshold is very important, which we will understand in our next class. So guys, is this clear to everybody, the process which we have just defined? Good. So for the next class, guys, I would want all of you to practice the data set which I have given. That's the climate data set. Okay. And also make sure that you find out multiple other data sets from online sources and practice your linear regression on top of that. And guys, once all of you have run the model on climate dataset, I want all of you to please email the snapshot of output, the final output, to contact@EquiSkill.com. Okay guys, everybody is okay with that? Great. And now before we wrap up the class, thanks a lot Amit for that. Before we wrap up the class, I think Amit, we already have the LMS link is there, right? Guys, you have on session 9, Amit, I can't see the feedback link. Okay, I'll refresh that. Yeah. Yeah. So guys, if you go to the session 9, there is a provide feedback link in there. I'm still pasting it in the chat window. I would request all of you to please provide your feedback before you leave from the class. So here is the link. Please go to the Google Forms, give your feedback and confirm it back to me once you have done that. In the meanwhile, I'm happy to take any questions which any one of you have. And as Amit mentioned, going forward, you guys can make use of LMS to access the feedback link. For now, please use the one which I have given in the chat box. And please provide the feedback as soon as possible. In the meanwhile, any one of you have any questions, please ask. Guys, I've just got one feedback till now. Others, please make sure that you provide the feedback. It's a request. The count's going up, 2 till now. What about others? Thanks a lot, Chandra, for the feedback. I'm waiting for others to confirm. The count's going up again, 3. Thanks, Hiroki. I've got 5. We still have 9 participants, 4 more left. Thanks a lot, everyone, for providing the feedback. I hope the session was useful. You guys learned a little, at least a little out of the session. Guys, I've got 6 feedback till now, 3 more pending. Thanks, Joshua. Thanks a lot for that. Thanks, Azita. Just 1 pending, guys. 1 of you are left now. Thanks, Kaustubh. Thanks a lot for your feedback. Great, guys. Thanks a lot, guys, for your time today. And, I think Amit will take over. He would just want to talk to all of you for 5 minutes.
All right. Thank you, Ujjwal, for that excellent class. I really appreciate everyone's participation as we get deep into the topics of analytics and linear regression. And coming up in the next class, we've got logistic regression. So what I'm going to do is see if I can share my screen now and make myself the host and very quickly share a couple of things with you. All right, here we go. So I'm the host now. As you can see, we've got a full-blown LMS, and you now have the data sets, the feedback links all in the LMS. We are on session number 9, class number 9 today out of what should be 16 classes. And class number 10 is on Saturday, the 1st of April, which is logistic regression. Now, what we need you to do for that class, one is the pre-work for the class today. You did that. You need to submit, your assignment, which is the climate change file. You need to analyze it and send across your screenshots to contact@EquiSkill.com. The other thing is, if you click on session number 10, and I'm going to do that now, you'll see a link called presentation and materials. And in this, you will see a document called logistic regression. So I don't know if you've had a chance to read that. You do need to read through this entire document. It'll make a lot of sense after everything that Ujjwal has taken you through today. You want to actually read this document before you step into the class today. Step into the class next week. We will also have the feedback link up and going very soon for class number 10. Okay, the Zoom link to join the class next week is already active. So if you click on this link that you see here on your screens, it'll automatically make you join the Zoom class for next week. Now, right now it's not working, so but this is active already, right? And similarly, we'll have the link for session 11 active in a very short while, right, for everyone. So you will find everything that you need in the LMS, and now onwards, mostly all that you'll receive is a message or an email, but really everything will be in the LMS, like you can see here for session number 9. You might also note that the earlier session, session number 8, the videos are already up. Session 7, linear regression, session 6, Tableau introduction. All the class videos have been loaded here, along with the presentations and the data corresponding to that particular class. So it's really a single point of reference for you. All that you need to have is this particular link, which is the LMS link, and that's it. You're up and going. So thank you everyone for joining up. Arvind, Joshua, Azita, Chandra, Karina, Kaustubh, Sridhar, Sundaram, Venkat, of course, and good night. I really enjoyed your participation. And Arvind says, this is great, Amit. Thank you so much, Arvind. And I think Venkat had earlier shared that this LMS link is far better than the one that we had in the previous batch. We'll strive to make it even better and get more information here for everybody, right? Everything that you need needs to be here on this link. That's all. You don't have to go anywhere else. Okay. All right. So Azita says thanks, Amit and Ujjwal. Joshua says thanks, Amit. Oh, thank you so much, Joshua. Azita, good night to you. Good night, Kaustubh. And to the rest of us, have a great day. So Karina, have a great day. I had a few in Eastern time zone, and I think Hiroshi already logged out. So a good day to him and Kavita as well. All right. Thank you so much. We're going to close the session now. The video should be up very quickly. I'm hoping to get it up tonight itself and paste it on this link. Okay. Thank you.